In this video, we're going to talk about rate laws now. How concentration of product in reactants can affect our rate. So for this, we're just going to look at a reaction where A goes to some products. It really doesn't matter. It doesn't matter what A is. Doesn't matter what the products are. But we can write our rate for this reaction in this form, where rate equals K. K is some rate constant. It will usually be given to you, and it's dependent on each type of reaction. So K is always changing. Multiplied by our concentration of A here, raised to the power of some integer n. N is order, and it'll tell us how, when we change the amount of A, how does our rate change. Okay, so let's just look at the reaction order in a little bit more detail now. As I said, reaction order is that N. And when you have a rate that has a lot of molecules in it and a lot of exponents, you can add all those exponents together, and the sum of that number is called the order of the reaction. So for example, if we have a rate law that's rate is K, NO raised to the power of 2, O2 raised to the power of 1, remember, we don't actually write 1 here. If there's a 1 there, it will just be blank. We say, well, this reaction is second order in relation to NO. We say it's first order in relation to O2, but overall it is third order because it is 2 plus a 1 here. So this is a third order reaction rate. All right. So let's look at the three numbers that N can really be theoretically. So the first number is 0. If N is 0, then it's a 0 order because, it's just you have a 0 there, right? So what does that mean? So that means if you double the amount of A and it's 0 order, the rate doesn't change. Because remember, anything raised to the 0 power is 1. So if you have 2 here, 2 raised to the 0 power is 1, your rate is K. If you have 4 for this A, 4 raised to the 0 is 1, rate is K. So rate is always going to be K in the 0 order. If this N is 1, it is first order, and that means your rate directly is proportional to your concentration. So let's go back to our examples of 2 and 4. If A is 2 here, 2 raised to the power 1 is 2, our rate is 2 times this variable K. If A is 4, 4 raised to the power of 1 is 4, our rate is 4K. So you saw we doubled the amount of A, and so our rate of reaction also doubled. So they're proportional. Now, if N is 2, that's a second order. That means the rate is proportional to the square of the reaction concentration. So if A is 2 again, 2 raised to the power of 2 is 4. Our rate is 4K. Now, if A is 4, 4 raised to the power of 2 is 16. Now it's 16K. Even though we doubled the concentration, our reaction rate has sped up by 4 times because 2 squared is 4. That's what it means to be proportional to the square of the reaction concentration. And our rate order is never going to go above 2. For reasons that we'll talk about later on, but the only 3 numbers you really have to deal with right now are 0, 1, and 2. Right, and here's graphical representation of what is going on there. So here is just concentration of A on the Y and time on the X for 0 order, first order, and second order. So 0 order is a linear decline. First and second order, you have a curved decline. But if I was to give you this graph of reaction concentration versus time, you could tell if the reaction was 0 order because the A would be a straight line. But let's imagine that you saw a change of A over time and it was curved. Now, if you only had one line to go on, you couldn't tell if it was first order or second order. The way you tell if something is first order or second order through a graph is that you measure the rate versus concentration. So zero order, rate never changes on concentration, so it's a straight line all the way through. For first order, they're directly proportional, so it's a diagonal line between rate and concentration. And second order, it is proportional to the square of the change, so you have this curved line. So if you were given this plot and given any three of these lines, you should be able to tell me if it's zero order, first order, or second order reaction. Now this is very important, so keep this in mind. You have to determine the rate law experimentally. The rate law has nothing to do with stoichiometry coefficients. So I can give you a reaction, I can give you stoichiometry coefficients, but you cannot, and I stress this again, you cannot look at the reaction and tell me what the rate law is. It does not work that way. What you have to do is experimentally, you have to do this reaction in very short intervals and vary your starting concentrations of your products. And by varying the starting concentration of your products, you can deduce if something is zero order, first order, or second order. So if you want to do this for multiple reactants, it's just like what we talked about. You have to determine the rate order experimentally. And to do this, you're going to hold one reactant concentrations the same while varying the second concentration and measure the rate. Then you can determine the rate order for the second concentration you're varying. Then you just do the reverse. You hold the second concentration's amount the same and you vary the first concentration, determine the rate, and since you know what the change in concentration was because you are doing this experimentally, you physically put in the amount of reactant, you can determine the rate of your experiment. That's it for this video, and I will see you in the next video.